All right, so our next speaker needs almost no introduction here. Somebody I've known for about 10, 10 years ago, I was like, hey, I need to do some art training. Called up our studio. I was like, hey, do you know somebody? They're like, yeah, called Art for Everyone. Really fantastic dude. Worked with him quite a bit, and also interesting fact about him, he's an expert in lacrosse, loves ice hockey, and even plays curling, but he is not Canadian. Ladies and gentlemen, Jared Lander.
Thank you very much. Thank you everyone for being here. Today, we are going to talk about a bunch of different models and see which ones work best. We're going to do a model shootout here. So what are we going to model? We need data. If we're going to model something, we need data to model. So we are going to use credit scoring data. Why? Because we have it. And nothing has ever gone wrong from giving someone a credit score. So our data looks roughly like this. We have a status column that is good or bad, and that's what we are trying to predict, whether you're good or bad. Your whole life's going to boil down to that. And we have other input variables such as seniority, if you own your home or you rent it, what your marital status is, your age, all this different stuff. And we're going to predict that status. That's the goal. So we're going to do this with a bunch of different model types and see which one is best. We will look at penalized binary regression, decision trees, random forests, boosted trees, boosted pseudo-random forests, and neural networks. And we're going to step through each of these, learn a little bit about the math of them, see what we have to do, and then we'll go and run them all. So how are we going to validate this? If we're going to say which one is the best, we need a way to decide what is best. We need to decide on a metric. So we are going to use AUC, area under the curve. It's a nice number for binary classification, and essentially it's between 0 and 1. You want it closer to 1. Nice and easy to understand. This plot shows it right here, sort of summarizes it. It's a balance between false positives and true positives. And in this plot, you want it drawn as close to the top left as possible, but we'll get down to a number. We will use cross-validation to tune the models, and then we will ultimately test the model on a held-out test set. And that, whichever one does the best, has the best AUC on the held-out test set, that is the winner. All right? So let's start with penalized binary regression. You are trying to solve this equation. You're trying to minimize this top equation. It is log loss, which is another measure of how wrong or good your model is, subject to a penalty. That penalty, the amount of penalty is controlled by lambda, that's a tuning parameter. And then in the second equation, the penalty can be split between L1 loss or L2 loss. You might also call these lasso loss versus ridge loss. And altogether, penalized regression, you might also call it GLIMnet or elastic net. There's lots of different names, but the goal is to minimize this top equation, which really just comes down to constrained quadratic optimization. It's a Lagrange constant in there, so it's nice and easy to use. There's a bunch of feature engineering for the basic stuff to get started. You need to make sure your class size is balanced. You don't want one class to be completely different than another class. You need to impute missing data. That means for numerics, you need to fill in a number. For categorical data, you could just label it missing, and that actually works nicely. You need to normalize your numeric data so everything's on the same scale. You need to deal with unknown data. What happens when it comes to prediction time and you have a level you haven't seen before? You have to deal with all that, and you have to convert your categorical variables to dummies. And you need to include an intercept. Now, of course, there's a lot more feature engineering you can do for your specific use case. But these are the basics you need for this type of model. So I've got to show you some code. I'm showing you the best language in the world here. I can't not show code. And these are the steps you would take using the recipes package to do all those steps. 9 lines of code to do all that feature engineering. Nice, easy, ready to go. Now, with all machine learning, we have tuning parameters. The main ones for a penalized regression, in fact, the only two for the most implementations, are the amount of penalty, how much you're going to shrink your coefficients, and what type of penalty, the mixture. And you can set those using the parsnip package. And here I'm actually only going to tune penalty. You'll see it says penalty equals tune. Mixture, I'm setting to 1 because I don't want to bother tuning it. So it's purely lasso regression, purely L1 regression. So that's the penalized regression. Then we come to decision trees. Decision trees have been around forever. They're recursive partitioning, really, really popular algorithms. And this is the equation for it. The idea is that you break up your input space your feature space into a bunch of discrete regions. And then in each region, whichever class is predominant, that's the predicted class. Really simple equation. The real magic of this algorithm is how you create that space. If you were Don Draper in the 60s, you would create buckets automatically by saying ages 18 to 24 and 25 to 35. But since we don't have Don Draper, we have machines tell us what these regions are. Feature engineering is a little simpler here. You need to make sure you balance your class size, and you need to impute missing data. Here we see the steps similar to what we saw before. There's fewer of them now. The main thing is the downsampling, and I'm doing downsampling, not upsampling. That's something we could discuss another time. And I'm imputing based on k nearest neighbors. Tuning parameters. There's also only really two tuning parameters you need. Tree depth, which is how complex any one tree can be, and minimum node size. That is, how many observations need to fall in one of those regions in order to make it a final region. And we could set that here with parsnip again. Again, I'm only going to tune one of them for the sake of time. I'm doing tree depth, and I'm using the partykit package because it should be faster than the rpart package. It's a faster package to use. One of the problems with decision trees, though, is high variance. And one of the first attempts to get away from that is a random forest. Why fit one tree when you can fit hundreds of trees? The idea is that you're going to fit hundreds of independent trees, each one randomly built, then average the predictions together. Now, if you're fitting a tree on the same data set, how do you make it random? There's two parts. Remember, in each tree, you're asking a bunch of questions. Is it bigger than this, smaller than that? Each time you're going to ask a question, instead of observing all the rows of the data, randomly sample half the rows and ask the question. Another thing decision trees do is if you have 50 variables, it examines all 50 variables for each question and says, which is the best to make a split on? And it decides. Well, here we're going to constrain it to say, here are randomly chosen 4 variables. Which one of those do you want to make the split on? So we've introduced 2 levels of randomness, randomly selecting rows for each tree and randomly choosing which columns you'll even consider for each time you're asking a question. So there's a lot of randomness. And random forests were designed originally to not need tuning. All right, we're not tuning it. We're doing feature engineering. I'm sorry. Balance. So the things you have to do here is balance the sample sizes and fill in missing data. You don't have to worry about dummy variables, just like with trees, which is really awesome. So it's the same steps as a regular tree. We saw this before, the same bit of code we saw before. So now I'll get to the tuning parameters that I was talking about when you didn't need to tune it. Leo Breiman designed this so you don't need to tune them. But we're going to tune it nonetheless. We're going to look at how many trees we want to average together. That's the number of trees. We're going to look at the minimum node size for each tree, how many observations have to be in a node. And we will try a bunch of different values of how many randomly selected columns do we want to examine for each split. We'll see here, I'm going to tune over mtry, which is the number of columns, and the number of trees. And I'm going to use the ranger package, get it, forest ranger. I'm going to use that instead of the random forest package because it should run faster. Another attempt to make trees better is by boosting them. Now you can boost anything, right? You could boost a linear model. In fact, it was originally called GBM, which is gradient boosted machines. We just so happen to boost trees today because that's just the best, it works the best, right? We're going to boost the trees. And the equation is deceptively simple. The prediction for the 100th tree is the sum of all the previous predictions, right? But that really does not give it justice because each tree learns from the previous trees. When you make your first tree, you make your predictions, well, the next tree learns from the mistakes of the previous tree and gets better. And it gets better and better and better for all these 100 trees, but you end up averaging everything together or summing them up all together, depending on your perspective, if you're averaging or summing, depending on how you formulate it. It's not really important, though. What's nice about boosted trees, at least this implementation of it, you don't need to worry about the class size. You don't need to worry about balancing the class sizes. You don't need to impute missing data, but you do need to convert your categorical data into dummy variables. So we're stuck with that, but hey, no big deal. We'll do that here for recipes. We have even fewer steps because we're not balancing the data. Nice, simple steps to do here. But what you gain in not having to do a lot of feature engineering, you make up for in tuning parameters. Yeah. There's tree depth. That's how complicated each individual tree can get. The number of trees is how many rounds of boosting are you going to go. The learning rate is how fast to jump to conclusions at each round. the number of columns, the minimum node size we saw before, minimum loss reduction. That means for each split in each tree, how much better the model needs to get. Sample size is how many rows you want to sample as a percentage. And stopping iterations, it's early stopping. Like, hey, if this isn't getting better after certain rounds of boosting, when should we stop? There's a lot you need to consider. I am just going to consider how many rounds and how deep the tree should get. I'm not going to worry about the rest. Now, remember I said you didn't need to worry about class balance? That's because XGBoost, which is what we're using, handles class balance for you. You'll see that scale pos weight. If I just give it the ratio of the overrepresented class with the underrepresented class, it calculates it for you. So I don't need to do any row sampling, it will do it for me. And you could use a different boosting algorithm like light GBM, which is actually, by all measures, supposed to be better than XGBoost, but everyone just keeps using XGBoost, so that's what I'm going to do. And a nice other feature about XGBoost is that I can do it on the GPU. All I needed to change was the tree method equals GPU hist, and now the GPU, which is really nice. You do need to install the GPU version of the package first, but that's actually relatively easy now, thanks to a GitHub issue I asked for like a few years ago. I asked them to build it automatically for us, and they said, sure. And that's all it took. Very nice and easy of them. So then we get to a boosted pseudo-random forest. You could boost your forests. It's not a true forest. That's why it's pseudo. You're basically combining the bagging of random forest with the boosting of a boosted tree. The reason it's not a true random forest is because we are going to sample the columns to consider once per tree, not once per question per tree. A true random forest would sample the columns at every question. This is just going to do it once per tree. Small sacrifice. So that, again, just like XGBoost, there's no need to balance class size, no need to impute missing data, but you do need to convert your data to dummies. So same steps we saw before, nothing new here. And the tuning parameters are all the same as boosted trees, except there's one new one, number of parallel trees. If we're making a forest, how many trees do you want to do at one time? How many trees should be in your forest? There we go. All right. Up. I skipped ahead. Nope, that's it. And my clicker is not really going for me, so I'm going to skip the clicker for a second here. All right. So this is what we saw before. Same exact thing we saw as XGBoost. We're going to use the GPU. Everything else is going to be the same. In this case, I'm going to take 50% of the rows each time. And I'm going to, for the call sample by tree, I'm just going to set it to 4. I'm going to tune over the number of parallel trees, the number of boosting rounds, and the tree depth. On to neural networks. Everyone wants to talk about neural networks. Half the time you talk to someone, they hear AI, they think neural networks. They hear machine learning, they think neural networks. This is a very simple feed-forward neural network. It's essentially just a series of linear regressions with an activation function in between, something like a leaky ReLU. The idea here is you want to solve for all the W's, all the weights, your coefficients. That's all it is. It's just using guess and checking essentially to find those things. And really, I don't think it's as big a deal as people make it is, but if you get a really deep and a really wide one, you can do cool stuff for the right type of data. So the feature engineering, you need to balance the class size, you need to impute missing data, you need to normalize your predictors, and you do need to convert your categorical data into dummies, or better yet, make it into an embedding. All right. We're just going to take the simple route here. This is a step you've seen before. You've seen this for many times. There's more steps involved now, but there's not done. You need to then go ahead and build a data loader. I'm using Torch here, but you can't just take your data and transform it. Now, the framework I've been using so far, parsnip, is part of workflows. Theoretically, that can fit a neural network, but it wasn't working well, so I went straight into the Torch code. So you have to do all these steps just to get your data ready. I'm not going to talk about it, I just want to show it. Now, the tuning parameters, there's a lot. The number of layers, the number of nodes in each layer, how much dropout you're going to do on your weights, whether you're going to batch normalize, which activation function you're going to use, whether you're going to sample your rows, are you going to put penalization in the form of weight decay? There's a lot. And to write this out, since we don't have a nice interface, you need to create your neural network from scratch. You need to build up all your layers. You need to put them all together. Look how much code this is taking. And that's not it. You then need to formalize it. You need to set it up and get it all ready. There's a lot going on. There's a lot going on here. It's just too much work. All right. So we have all of our different models. Let's put them all together. Let's draw the DAG. I'm not running all these by hand. I'm putting them all together in a DAG, and everything's going to go for us. For each model type, it's going to do the feature engineering. It's going to do the tuning with cross-validation. It's going to refit on the training data, the test data, and evaluate the AUC. This is our workflow. All right, this comes from the targets package. And when I want to run all these steps, I want all these steps to happen, I run this one line of code. Yeah, it's like make, but for R specifically. It's great. And it can run all your steps in parallel. Now you do have to be careful because some of our algorithms run in parallel already, so you don't want to do parallel within parallel. What's really cool is, at least with XGBoost, I can do the cross-validation in parallel on the CPU and have all the fitting happen on the GPU in parallel again. That's really awesome. All right, let's see how our models did. It's time we fit all our models. It ran really quickly, maybe, maybe not. And we will see how each of our models did. We're going to compare AUC for all of them in a nice, simple bar chart. And we see very quickly that the boosted pseudo-random forest is the best. Barely. Right? All of them are roughly, good traffic, all of them are roughly the same. But a plain old tree is a little bit worse. It's a little bit worse than all of them. And notice there's actually a difference between the boosted tree and the CPU and the GPU. There's probably a little bit of randomness, so we're not going to worry about that. And notice I'm not showing the neural network. Its AUC was 0.5. So I'm not, if I made it more layers, I tuned it longer and spent a lot of money on GPU time, I could have got it better, but it just wasn't worth my effort to do that for tabular data. If I were doing vision data or text or audio, maybe neural network would have been better, but for this tabular data, it wasn't worth my time. But now let's see how long the models took to fit, because that's an important part of the conversation. The boosted pseudo-random forest took a lot of time. 12 hours. Yeah. Now, that's not just fitting. That's the cross-validation and everything. But I wasn't doing that much cross-validation either. So let's take out the random forest, the boosted forest, and see how it did. This is a lot easier to see. The linear model was the fastest, about 4 seconds. That includes the cross-validation and the tuning. That's pretty good. The slowest was a regular forest at about 6 minutes. That's a lot better than 12 hours, right? So we really want to find the Pareto optimum of performance and speed. So we plot them together. We can see here that the pseudo-random forest is just throwing off the scale. So let's take it out and see this again. And now we can see it very quickly. It looks like both the linear model and the boosted GPU model are the best of both worlds. They're both accurate and they're fast. While a single tree was faster than a boosted tree, its performance is so much worse that why bother? And we can see here that the boosted GPU and the CPU versus the CPU, the GPU was faster. And since it was technically a little bit more accurate, random maybe, let's just go with that one, right? That's our best model. Linear or boosted GPU, the best. But there's one more thing. I want to ensemble all the models. I want to stick them all together. We are going to fit a weighted average of the different models. We're going to compute the weights by taking our true outcome variable and regressing that with penalized regression against the outcome from all of the models, and then see which ones should be weighted more heavily than others. We do that with this simple 8 lines of code by taking all of our models we had fit earlier, combining them together. But I'm not just combining these 6 models. I'm actually combining all the different versions of each of the models. So if I have for a single model 50 different parameter combinations, I'm actually ensembling those 50 models with the 50 for the other type and the other type. So I'm actually ensembling hundreds of models and seeing which ones are best together. And when we do that, this shows us the combined weights for each model type. So the boosted pseudo-random forest was used 3 times in our ensemble and had a combined weight of 4, which is nearly double all the other ones combined. No, it's the same as all the other ones combined. It's more than all the ones combined, barely more. And so it had the highest combined weight, it got used the most. So that was the most contributive, and I don't even know if that's a real word, but the most contributive to our ensemble model was this boosted random forest. And now what we're going to do is we're going to get predictions from all these models combined and see how they did on the test set and compute the AUC. And we see that the ensemble is indeed the best we had. Slightly, a little bit better, right? But keep in mind, though, that ensemble included that boosted random forest, which took 12 hours to run. So as you know what, let's do it again, but leave out the boosted random forest. And we see the slightly smaller ensemble model was just about as good. It's better than the pseudo-random forest by itself. It's better than everything else, and it's almost as good as the full ensemble model. So you know what? I'm just going to do that. I'm going to fit everything except for the neural network and except for the boosted random forest and ensemble them together. Since the ensembling process added about like another minute to the process, that's what I'm going to go for there. So of all that, we learned a lot of different things. We learned some math, we learned some code. So besides the math and the tuning parameters, what do we get from this? Now, linear models are fast and they're performant. Sometimes just go with a linear model and be done with your life and move on to the next problem. Boosted trees are a little bit better, especially if you use the GPU, then things are great. And we saw that we needed to balance the performance with the speed. One without the other is no good. You need both. But in reality, we're going to do what we're due and throw everything against the wall and see what sticks. And if you really want something good, you're just going to combine them all together. That's the key thing. Throw everything, combine them all together. Thank you very much.